Vijay was supposed to speak at this time, but he's not here today. So I'm Amritanshu Prasad, and I'll be talking about determinants today. I'm going to try to give a geometric definition of determinants and explain to you why it's the same as the other usual definitions of determinants. So firstly, let's try to understand what is a matrix really, geometrically speaking. So if you have a matrix A11, A12, A1n, A21, A22, A2n, I'm looking at a square matrix here. Then you can also think of it as a transformation. So for a vector x1, x2, xn, the matrix transforms it to a new vector, and that new vector is just given by matrix multiplication, right? So you just multiply these and you get A11 x1 plus A12 x2 AN1 x1. How to visualize this transformation? One way to visualize this transformation is to look at what happens to coordinate vectors. Coordinate vectors are the usual ones. I'm going to write all vectors as columns just because it's convenient then for matrix multiplication. So E1 is the vector with 1 in the first place, E2 is the vector with 1 in the second place, and so on. En is the vector with 1 in the nth place. So what happens to these coordinate vectors? If I apply this matrix to the jth coordinate vector, what do I get? So what you do is you would put zeros here, and only in the jth place you would put a 1. This is in the jth place. Well, right, so as somebody said, it will just pick out the jth column of this matrix. So A, if I call that matrix A, then AEJ is just A1j, A2j, ANJ, jth column of A. Therefore, the key to visualizing the transformation of a matrix that a matrix does is to somehow try to think of its is through its columns. Okay, let me just illustrate with a couple of examples. Let's look at the matrix 1 x 0 1. This is a matrix in the plane. It transforms the plane, and this is called a shear because what it does is you look at the first coordinate vector E1 and the second coordinate vector E2, and what does it do? It takes E1 to 1 0, which is still E1, but E2 it takes to x times E1 plus E2. So you would take E2 plus x times E1. So I'll call this E1 prime, the transformed vector, and it will become like this. And this distance from the y axis here is x, but the height is the same. So it will transform, if you want to give it a nice geometric thing, it's nice to just take the square, right, and it gets transformed into a parallelogram. So this is what this matrix does. This is called a shear. How about another example? What about this one? What will happen to E1? It will get stretched, it will go to 2, 0, so it will go to 2 times E1. So it will get stretched by a factor of 2. But E2 will remain the same because this is just 0, 1, which is E2. So this is stretching of the square into a rectangle. This is called a dilation. Dilation just means stretching. And let's look at a third one, which is my favorite matrix. What happens here? It takes E1 to 0, 1, that's E2, and it takes E2 to E1. So it looks like nothing much is really happening in terms of pictures, but the labels are changing. So this picture here is still a square, but the labels of the edges have changed. Okay, so these are just some examples. We could try to construct higher dimensional examples as well with 3 dimensions, but I'll maybe do that a little later. Okay, so I'll call this thing the unit cube. C equals, I wrote it in 2 dimensions, but you can certainly define it in any number of dimensions. Just take all the vectors x1, xn such that xi is between 0 and 1 for all I. So in this case it's just a square. In the 3-dimensional case it's really a what we'd call a cube. In the 4-dimensional space you may call it a hypercube or whatever, but I'll just use the general generic term C and call it a cube, okay, in any dimensions. So I've just drawn it for 2 dimensions, and here it is for 2, 3, 4 and so on. So now you can try to understand what a matrix does, how it transforms the space, by seeing how it distorts or changes this unit cube. Okay. And this is going to be so what does the matrix do? I'll write AC. So this will be the set of all A x. X is a vector where x is in the unit cube. And so that's the definition, and I'll define determinant of A as the signed volume. Signed volume. So this signed is a word that I'll have to explain. If I had just said determinant is the volume of AC, you would say that can't be, because some matrices have negative determinant. For example, this matrix, its determinant is -1. So determinant cannot be volume. There is some funny sign coming up. You can check in these cases that the determinants of these matrices are in fact the volume of the of AC. This is AC in each case. So this is really 2 times this thing, so its volume is 2, if you take this as volume 1. So, okay, so what is volume firstly? Right, I shouldn't have been using the word volume here, this is really area. In 2 dimensions it's just the area, in 3 dimensions it's actually the volume, and in higher dimensions it's some similar thing. If you want to really understand it from a precise mathematical point of view, one way to think about it is, in school we did this. Suppose I want to calculate the volume of some, so we had this, I remember, project in school where we had a leaf and we were asked to compute its area, and the method we were told was to put this leaf on some graph paper. And to count the number of squares that are fully inside the leaf and the number of squares that are at least touching some part of the leaf, and the first number, the number which is fully inside the leaf, would be smaller than the number of box squares which touch at least some part of the leaf. But for each of these squares we know their area, because we know the formula for the area of a square, just the square of its side. So we can write down the volume of the leaf. So there is some notion of outer area, inner area, and we know that the area of the leaf will lie in between those two. So what you do is, to calculate volume, one possible way is to divide the well, let's say area firstly. Divide the plane into squares, let's say of side 1 over n units. So if I take very big squares, I will get a very crude approximation of the area. If I take smaller and smaller squares, I will get better approximation of the area. And then you look at k is equal to number of squares inside the leaf little k is equal to number of squares touching the leaf somewhere. That means, for example, this square here, it's not completely inside the leaf, but some part of the leaf is intersecting it. So number of squares intersecting the leaf. And what you get is area lies between capital K over n squared and little k over n squared. And then you take the limit as n goes to infinity. And this is also what we teach as the definition of the Riemann integral in some sense. There we divide it into rectangles. We want to compute the area under the graph of a function. But also when you do measure theory, you kind of generalize this same notion. So this can be taken as a perfectly good definition of area, especially since we are not interested in computing areas of very complicated things. We are going to be looking at these kinds of cubes and their images. So these are parallelepipeds. And how do you do in higher dimensions? Well, then instead of the plane, you divide Rn, and not into squares but into cubes, hypercubes or whatever, of a side 1 over n. So if it's in a 3-dimensional space, you just divide it into cubes, and then you would look for number of cubes inside the whatever shape, and here you would look at the number of cubes touching the shape. And here what should I do? It's not n squared, but it's n to the power small n, capital N to the power small n, and then you take the limit as n tends to infinity. So certainly this volume has a very simple and concrete interpretation. So I'll just define the volume of a matrix A to be the volume of A of C. This is by first approximation of the definition of determinant. Now I need to explain what this sign is, because sometimes you get negative signs and so on. But let's just think about this volume. But before I go to sign, let me just do this calculation. So volume of this is 1. Volume of this is 2. More generally, I could have put any number here, any positive number at least, and the volume would be that positive number. And if I put 0, then the volume would be 0, because this would have no area really. And here the volume is equal to 1 again. And here the volume is not the determinant, it's the negative of the determinant. So there's something more to be understood here when we come to talk about determinants. But already this volume has some nice properties that the determinant has. And this can be shown geometrically. So I want to convince you that volume of A times B. Now A times B, one of the properties of square matrices is that you can multiply them. And what does that mean? Well, A and B, each of them is a transformation. So first, if you have a vector x, then what does this transformation ABX do? Well, you can write it, because matrix multiplication is associative, you can write it as ABX. So it takes, so if you take the cube here, then it will go to something B of the cube, and then you will again transform this transformed cube once again, and you will get some new thing AB cube. So it's A acting on, so instead of the coordinate vectors, now you will be using the transformed coordinate vectors E1 prime, E2 prime up to En prime. So that's what matrix multiplication is. It's really just applying B first and then applying A. Okay, B comes first because we are doing right multiplication by the vector. So here first you do B and then you do A. So now can you believe this, that volume of AB is volume of A times volume of B? Well, from this definition it's not completely obvious at first why this should be true, but let me try to convince you that this is the case. I'll give you a proof, in fact. So what we need to do is we need to see how this how to compute the volume of, this is really the volume of A of B of C. Now when we computed the area, what we used really was not so much that these are squares, but that these are figures whose area we actually know. So even if these were not squares, suppose we had used triangles, we could have computed the area. So the idea here is that we will try to compute the volume of A of B of C not by using squares, but using certain parallelograms. Let's just think about the case of the two-dimensional case for now. So what we have is that when we computed B of C, when we computed the volume of B of C, what we did is, firstly we divided the plane into small squares, a grid of squares, and then we saw that this B of C is in the union of some squares, C1 union C2 union CK, the squares which contain B of C, and in turn it contains some other smaller squares. So each of these squares is certainly, if it intersects, then if a square is contained in B of C, then certainly it intersects B of C. So this will be a subset of those squares, where this, so maybe I'll call this capital K and I'll call this little k. So we put B of C inside a union of these squares, and it contains the union of these squares, and then because we know the areas of these squares, we were able to get upper and lower bounds for the area of B of C. Okay, all I'm saying is these squares on the right are the squares which intersect, well, in the case of the leaf, which intersect the leaf, and the squares on the left are the ones which are completely inside the leaf. So here we also can do that for a parallelogram, and now let's apply A to this whole picture. So you get A of B of C. Well, this should be contained in AC1 union AC2 union ACK, capital K, and this should contain AC1 union up to AC little k. So, but do we know the area of this AC1? This AC1 is just the transformation of C1, but what is C1? C1 is just 1 over n to the small n, well, if you think of the plane, that would be 1 over n squared piece of the unit cube, right? So this has volume but that is by definition 1 over n to the n times volume of A. Right, I am just saying that see, I had this leaf and now these are squares. After transforming it, this leaf also gets distorted into some other leaf, but these squares get distorted into parallelograms, and they will no longer have area 1 over n squared. They will have some different area, but still n square of them will make up the cube A of C, because n square of these make up the cube C. So these things, AC1, AC2 and so on, they will have volume 1 over n to the power n times volume of AC, which is 1 over n to the power n volume of A. So what I get is that volume of A of B of C lies between volume of A times k over n to the n and volume of A times little k over n to the n, where this big K and little k are the same as the ones I got while trying to compute volume of B. So when you take the limit to infinity, this and this will tend towards volume of B. So taking the limit, you get volume of A, B, C is equal to volume of A times volume of B. So in particular, you get this, volume of AB is volume of A times volume of B. So because this matrix multiplication is given by composition of transformations, the volume becomes multiplicative. That's the basic idea. I hope that's clear, because the next point is a little more tricky to understand, and this is this question of what is this sign about. Now suppose I draw a hand on the board. Can you tell me, is this a left? Oh well, I need to give you some more information. So this is the palm of the hand. You're seeing the, yeah, I need to put in all that. So this is the palm of a hand. Can you tell me, is this a right hand or a left hand that I have drawn on the board? It's a right hand. And if I put a mirror, then I'll get its mirror image, and that's a left hand. Okay, but yeah. But really, so are they so different? I mean, I just drew a picture. I didn't show you the person who has it, but you could still make out that it's a right hand. So there's some serious difference between this right hand and its mirror image, right? But look at other things. Take this bottle. Suppose it doesn't have this label which says whatever, and I look at its mirror image, then there's really no difference until you try to open the cap. When you open the cap, this one will open when you turn it anti-clockwise, whereas its mirror image will open when you turn it clockwise. So there's some objects in this universe, in fact I would say most of them, which have a certain right-handedness or left-handedness. They are not the same as their mirror images. Can you think of other examples? What about my wristwatch? Yeah, because it has this key here. Well, of course it also has these numbers, but ignoring that, just this key will make sure that it's not the same as its reflection. I am fairly symmetric, at least from the outside. So objects which are not the same as their mirror images, they are called achiral objects. This comes up if you teach chemistry, then you'll be talking about achiral molecules, right? You can take a carbon and put 4 different radicals on it, and that will not be the same as its mirror image, and they would have different chemical properties as well. So this is something which is really pervasive in this universe, and the determinant also captures this. So what do we need to realize about this is that when you reflect something in a mirror, this property, which I'll just call chirality, changes. So chirality changes when you reflect something in a mirror. Okay, and let's just look at my favorite matrix now. And suppose I were to draw a hand here. So I'm finding it a bit hard, so I'll just draw a schematic diagram of a hand. So that's a hand, and I guess that's a left hand, assuming that the palm is always facing you. But when I interchange E1 and E2, it's as if I'm reflecting about this line x equals y, right? E1 goes to E2, E2 goes to E1. It's just reflection about this line. And so what happens to this hand is it becomes a right hand. So left hand becomes a right hand. That's my left hand, that's my right hand. So chirality changes, and that's what this sign is. So I'll define sign of A to be 1 if chirality is preserved, -1 if chirality is reversed. Okay, but this is just a reflection. Maybe I could do some very complicated thing. I could shear, dilate, and then reflect. would chirality be preserved or would it be reversed? We all of us have the ability to recognize chirality. Let me illustrate with examples from the English alphabet. So there are 4 letters which look quite similar: B, D, P and Q in the lower case. B and D, but I don't want to talk about P and Q. Let's say everything is either a B or a D. P and Q is not allowed. So I'll draw various things and you tell me whether it is a B or a D. So I can shear this. So what happens? It becomes something like this. Is this a B or a D? This is still a B. It looks a little different. I can shear this. This is still a D. What about this thing? Is this a B or a D? This is still a B because I can just rotate it, but I cannot make it a D. No matter what I do, I can't really turn this into this. So this goes into this first table, and this will become like this. The D will become a P. But actually, if I wanted the mirror image of this, I could have also done. This is still a shear in the other direction is also still a D, and this is the mirror image of this, and the mirror image of this is a shear like this. Right? So all the things on the left of this line are B's, and all the things on the right of this line are D's, and they are related by mirror images. So that's so there are some transformations which preserve chirality, and reflections reverse chirality. So let me just so what we've seen is that I can also take the B and make it very fat. That's still a B. You can all recognize it. This is still a D. It's a fat D, but it's still a D. Nobody will say that it's a B. So there are some things which preserve chirality. Shears preserve chirality, and dilations, when you have a positive scalar, they also preserve chirality. So shears and positive dilations. As I don't want to think about a matrix -1 0 0 1. Preserve chirality, and partly the reason is that you can go from this figure to this figure. You can morph it continuously. I can start with a square and then start shearing it a little bit and shear it more and more and more till I reach here. So there's a continuous path from here to here. And the same from here. I could start with this square and I could try stretching it more and more till it goes there. Here, if I were to try to interchange these two basis vectors, well, okay, you would say maybe I could bring them closer and closer together, and then I could reverse their direction. But then there will be one point when those two vectors coincide, and at that point they will not be linearly independent. And that somehow is not, when you take both these vectors to one vector which is not linearly independent, that's not an invertible linear transformation of the plane. And so you can't continuously go from this to this without passing through at least one singular linear transformation. So there's also this idea of connectedness behind preserving chirality. If you can go from the identity to your transformation, from the identity transformation to your transformation, a continuous family of all invertible transformations, then there's no change in chirality. That's one of the facts about chirality. Okay, so now let's just now we are ready to see why this should match up with all our other notions of determinants. So I think I've, oh yeah, but let me just talk a little bit more about reflections. So what are reflections in higher dimensions? So so let's look at some three-dimensional examples. So let's look at this matrix 0 1 1 0 0 0 0 0 1, and now I need to draw figures in 3 dimensions. So I'll draw the picture. Probably need a little more space. Maybe these B's and D's can go. So here, what does this do? Let's see. So let me draw my 3-dimensional coordinate system E1, E2, E3. So this is the x direction, this is the y direction, this is the z direction. And what does this do? This takes E1 to E2, right? 0 1 0 is E2, and it takes E2 to E1. The second column is 1 0 0, that's E1, and it doesn't do anything to E3. So really this will go to this will get transformed to a similar picture, but with just this will be E1 prime, this will be E2 prime, and E3 prime will just be E3. So is this a reflection? It's a reflection. So in 3 dimensions, see, in 2 dimensions reflection is just in a line, right? So these are 2-dimensional representations of hands, and the deflection is a line. In 3 dimensions the mirror is a plane, so reflection should be in a plane. So what is the plane in which this is a reflection? It's just the plane x equals y. X equals y is a plane in 3 dimensions, all the points x, y, z where x is equal to y. So this is a reflection in the plane x equals y. If you look at a matrix like this, now this time I'll leave E1 the same, but I'll interchange E2 and E3. If you look at this matrix, then this will be reflection in y equals z. So these, I'm interchanging the second and third coordinate vectors. So all these matrices where I just take the identity matrix and interchange 2 columns, these will correspond to reflections in certain planes. You can do the same thing in higher dimensions. You know, you can take a 4 by 4 matrix and interchange 2 columns. That will be a reflection in some hyperplane, but it's hard to visualize. In any case, these will all be chirality reversing transformations. So here are some chirality reversing transformations. What about this one? Suppose I take -1 0 0 1. Is this chirality preserving or chirality reversing? It's chirality reversing, because if you look, draw the picture, then what it's doing is it's taking E1 to minus E1. And just to make sure, let me draw a hand. Well, okay, yeah, so this hand, it's actually reflection about the y-axis. This hand, which is a left hand, will become a right hand. Right, so that's chirality reversing. So if you also, so what we saw is if you interchange 2 columns, that's a reflection, but also if you just take one of the columns and change the 1 to a -1, that will also be chirality reversing. If I had, if instead of the first of these ones I had taken the second one and made it a -1, then what that would do is that would change this to, that would change E2 to minus E2, and this hand would become like this. So this hand would become like this, and then it's certainly a right hand, right? So it's also chirality reversing. Both these are chirality reversing, and in general you could do this in higher dimensions. You could take a matrix with all ones and then you just put a -1 somewhere, and that will be chirality reversing. So what have we done? We've defined determinant as a signed volume. The sign is 1 if chirality is preserved, -1 if chirality is reversed. Volume, of course, we all understand quite well, and we've also listed some things which are chirality preserving, namely shears and dilations, and we have also said that all kinds of reflections are chirality reversing, and in particular there are two kinds of reflections which we will be interested in: interchanging two columns or changing one of these things to a -1. Okay, so this is what we have done so far. And now, using this much information, I want to convince you that this geometric definition that I have given for determinant is not really different from the definitions that appear in algebra textbooks. And so in algebra textbooks, how do you usually define determinant? Well, the most practical way to define the determinant is to tell you how to calculate it. So you can calculate the determinant using row and column operations. Certain operations preserve the determinant, certain operations change the sign, and certain operations you multiply the determinant by a scalar. Oh yeah, one more thing I want to say is that this sign is also multiplicative. So sign of AB is equal to sign of A sign of B. So this, of course, if two things are chirality preserving, then their composition will also preserve chirality. If a right hand goes to a right hand, and then the other thing also takes a right hand to a right hand, then right hand goes to right hand goes to right hand. Whereas if both are chirality reversing, then their composition will be chirality preserving, whereas if one is chirality preserving and the other is chirality reversing, their composition will be chirality reversing. So this is also needed, and so in effect what we have shown is that determinant of AB is determinant of A times determinant of B, because we have also shown that volume has the same property. So volume has this property, sign has this property, and determinant is the product of volume and sign, so determinant also has this property. So this is sort of a geometric proof of the multiplicativity of determinants. And now let's just show that this notion of determinant has the right properties with respect to row and column operations, and that should be enough to show that it coincides with any other definition of determinant, because you can take any matrix and perform these elementary row and column operations and reduce it to some canonical form for which we know the determinant. And so let me just give you an example. So let's start with this matrix 2 1 1 0. So let me first try to okay, so I'll try to compute its determinant from what I know. So I can do some row operations. I can, for example, I can try to make this I'll try to make this 2 into a 1 firstly. So 1 half 1 0. But what was the cost of doing this? Well, it was as if I had to multiply this matrix by half 0 0 1. So this matrix is equal to this matrix, the product of these two matrices. Just check. No, sorry, yeah, 2, right. So left multiplication by 2 0 0 1 is the same as just scaling the first row by a factor of 2. So I have made this 1. Now I'll use this 1 to eliminate this and this. So now I'll do 2 0 0 1. I am carrying this along, and now I will try to subtract the first row from the second row. So I will have 1 half 0, and then I must subtract the first row, so I will have minus half. And what was this operation corresponding to? This was corresponding to, I am not doing anything to the first row, but to the second row I am subtracting the first row. And you can check, nothing happens to the first row, it remains 1 half, but here I get I should probably put a 1 here. Okay, so yeah, so 1 plus yeah, that's 1, and that's half minus half, that's 0. Okay, so this is this, and then let me just make this kill this guy. So what should I do? I should if I don't want to disturb this, probably the best thing to do is to subtract half times the first column to the second column, and that will correspond to some right multiplication. So I still carry down all these things. One half 0 minus half, and then I want to make this 0, so this would be 1, first column doesn't change, second column is so I must add the first, so maybe I should put a minus 1 here, 1, so I'll get minus 1, second column, right, so minus 1, that doesn't quite work, so minus half and minus half. Yeah, is that correct? Okay, and then finally I'll just make this 1 0 0 1 times, well, never mind. Okay, so what I found is that this complicated matrix that I was starting off with is a product of all these matrices. And what's so special about all these matrices? This is a dilation, this is a shear, this is one of the scalars is multiplied. Actually, maybe it's better if just for if I write this like this. So I'll do one last step. Okay, so this is a dilation, this is a shear, this is a reflection, remember, this is another dilation, and this is another shear. And so for all these I know the determinant, and I know that the determinant is multiplicative. So I have that the determinant of this matrix is the product of all these determinants. So determinant of this is, so this has determinant 2 times, 1 times, minus 1 times, half times 1, which is minus 1, right? And of course you can calculate it with your favorite formula for determinant, 0 times minus 1. So what is the principle here? What we were really doing is a row and column reduction of this matrix to this matrix. If you or if you want, you could say to the identity matrix, right? So and using only matrices whose determinants we know. And each time we do a row or column operation, something happens to the determinant. So this time when we did the row or column operation, the determinant became half, because we divided, actually here I am writing the product, but actually what we did was we divided this matrix by this matrix. So each time you do an operation to this matrix, the determinant changes by the determinant of the matrix of the operation which you are doing. So what you see is that elementary row and column operations correspond to left and right multiplications by matrices whose determinants we know. Elementary row and column operations. Correspond to left is for rows and right is for columns by elementary matrices. And these are shears, reflections, dilations. And by reflections we only need two kinds of reflections, the ones which interchange two columns and the ones which replace 1 by a minus 1. And for these we know the determinants. So using this you can show that the determinant that I defined using signed volume has the same properties that whatever determinant you define in your algebra textbook has, that is scaling a row, maybe I'll write it schematically. So if you take Cj goes to A Cj, then determinant goes to A times determinant, right? If you do Ri goes to A Ri, then determinant goes to A times determinant. See, if A is positive, then this is just the property of the volume, but if A is negative, you can think of this in two steps. First you scale it by the absolute value of the A, and then you scale it by minus 1. Scaling by minus 1 is a reflection, so then you will again get minus absolute value, which is A. So in the negative case you can do it in two ways. And then if you interchange Ci or Cj, or if you interchange Ri or Rj for two distinct rows or columns, then determinant changes sign. And then if you take a column and add to it some scalar times another column, then determinant remains determinant. And the same with rows. And because I can reduce any matrix to a matrix of the form 1 1 1 and maybe some zeros, or actually by these operations, and for this I'll know that the determinant is 1 if all these things are 1, and 0 if there's even 1 0, because it's then making some of the coordinate vectors go to 0, so you can't actually get non-zero volume. So using these facts you see that this is exactly satisfies the same conditions that whatever algebraic definition of determinant that you have in your textbooks. So this geometric way of thinking about determinants, actually I hope I've convinced you, gives you exactly the same definition that you would have in standard algebra textbooks. Okay, and the Russian mathematician Arnold says that this is the only correct way to define determinant in terms of teaching, that when we teach we like to think in a certain way, and I don't know, this is probably debatable, but most of us think fairly geometrically to start with, and this algebra comes as a part of training. And also a lot of mathematics is comes from trying to model problems in physics where we need to really think geometrically. So in that sense a proof that is a definition that is geometric has much more relationship to the physical world around us, and also perhaps gives us a better intuition about the object that we are studying. You see, this proving the multiplicativity of determinant was quite natural using this volume thing. right? If you compose two things, the volume should get multiplied. In the algebraic proof, it seems maybe a bit like a miracle that the determinant is multiplicative. So it's good to also have this kind of geometric picture in mind, and maybe at least in the back of your mind when you're thinking about determinants. I hope you found this somewhat helpful. That's all I have to say, but if you have questions, please. Well, okay, I guess if there are no questions, we can just stop now. Thanks.